Welcome to the course of structure analysis. In this lecture, we are going to see what are the different deflection formulas are there for a cantilever beam, which is subjected to a different loading conditions. Firstly, I'm going to tell what are the different methods that are there for finding the deflection of the determinate beams. Here, the determinate beams can be cantilever beams, simply supported beams, and overhang beams. So first method is double integration or Mechle's method. Second is moment area method. Third is conjugate beam method. Fourth is strain energy method. Fifth, Castigliono's method. And then unit load method. So these are the different methods that we are going to use for finding the deflection of the determinate beams. Now I'm going to consider a case for a cantilever beam. By using a double integration method, we are going to solve for a slope and a deflection. So like this, you can use any of this method and you can find out the deflection for the beams. So coming to the next, here we are going to derive deflection of a cantilever beam subjected to a point load at the free end. So this is a cantilever beam which is having a point load at the free end and the span here is length L. I'm using here the double integration method. So the double integration method, the equation here is A into d square y by dx square will be equal to minus mx. So for same this beam I have drawn here. And here we can see that I cut a section at this portion, which is from the B support. So at B, I'm taking the origin, that is x is equal to 0. And at A, I'm taking x is equal to L. So the limits here are 0 to L. So when we cut a section at this portion, there is a x distance from the B support and the remaining distance will be equal to L minus x. So whatever the slope I'm having at this B support is theta B and the deflection here is y max we are writing and it can be yb also. Actually, yb is maximum because at the free end we are having a more deflection. So we consider, as I already told you, by considering a section at this portion. Now writing the mx equation. So the mx equation will be equal to, as you are having the load to be downward and towards the section, the arrow is heading downwards. Therefore, it is in the hogging nature. Therefore, it is minus w into x as per the sign convention. Now I'm going to substitute this mx equation in the above equation, that is ei into d square y by dx square will be equal to minus mx. Therefore, you are going to get it as plus w into x. So after getting this equation, I'm going to integrate it once. Then I'm going to get ei into dy by dx will be equal to wx square by 2 plus c1. So this part I'm going to integrate it. So here C1 is nothing but your constant of integration. So this is your slope 1. dy by dx is nothing but a slope. So after getting that equation, what I'm going to do is we are going to find this constant C1. So to find the constant C1, we are going to use the boundary conditions. So the boundary conditions are at x is equal to L, we are having slope equal to 0. So that is dy by dx equal to 0 since the support is your fixed support. So by substituting the above, I got C1 as minus double L square by 2. So we are going to substitute this C1 in this above equation. So therefore we are getting the equation to be ei into dy by dx will be equal to wx square by 2 minus double L square by 2. So this is a slope equation. So by using the slope equation, you can find slope at any point of the beam. From x is equal to 0 to x is equal to L, we can find the slope. So if you substitute x is equal to 0, I'm going to get slope at the B point, that is minus double L square by 2. So for suppose if you want at x is equal to L by 2, we can substitute in the place of x, we can substitute the L by 2 value. After this, just I substituted x equal to 0 and I got dy by dx is theta b. So as I already told you, theta b is minus WL square by 2EI. So this is a slope at this B point. And next case is, again, to get the deflection at this portion, what I'm going to do is I'm going to integrate the slope equation. So this is the slope equation we got. So once again, we are going to integrate it. So if you integrate this dy by dx, we are going to get it as y. So that is EI into y will be equal to, so wx cube by 6 minus WL square by 2 into x plus C2. So C2 is another constant. So again, we are going to use the boundary condition at a fixed support. So as it is a fixed support, the x is equal to L, we have y equal to 0. By substituting these values, I got C2 value to be WL cube by 3. So after getting the C2 value, we are going to substitute at this place. Then I got the equation as EI into y will be equal to WX cube by 6 minus WL square by 2 into x plus WL cube by 3. So this is a deflection equation. Same way, when this equation is valid for x is equal to 0 to L. So you can substitute the x value at any point and you can get the deflection value at that section. So now we are going to find deflection at this B support. So now you are going to substitute x is equal to 0. I am going to get deflection at this portion, that is y is equal to YB. We get YB value as WL cube by 3EI. So this is a deflection at this B support. You can see here the downward deflection at this B support is given by WL cube by 3EI. So here positive indicates that the deflection is in downwards. So this is how you are going to derive a deflection formula for a cantilever beam which is subjected to a point load at the free end. Likewise, you can derive for any case. Just a sample one I have just told you. Now we are going to see the deflection formulas for different loading conditions of a cantilever beam. So as we already derived, when we are having a point load at the free end, the deflection formula is WL cube by 3EI. When we have a point load at the eccentric distance, then we have the deflection at the free end. This is your free end. That will be equal to WA square into 3L minus A by 6EI. Similar way, when you are having a point load at the center, then the deflection formula at this free end will be equal to 5WL cube by 48EI. And when we have a UDL overall the span, throughout the span, the deflection formula at this free end will be equal to WL power 4 by 80EI. Similarly, there are still some more cases are there. When we have a UDL up to a certain portion A from the fixed support, the deflection at the free end will be equal to WA power 4 by 80I plus WA cube by 6EI into L minus A. When we have a uniformly varying load, which is having a maximum load at fixed support and zero load at the free end, then we are going to have the deflection formula to be WL power 4 by 30EI. Same thing, but in a reverse fashion, that is UVL varying from 0 to W. So 0 at the fixed support and W intensity load at the free end. Then the deflection will be at the free end will be 11 WL power 4 by 120 EI. Next, when we have a cantilever beam at the free end, when we have a moment, the deflection at this free end will be equal to ML square by 2 EI. Similar way, there are some other cases when we have a moment at some distance from the fixed support, the deflection formula at the free end will be equal to MAL by 2 EI. Similar way, when we have a up to some portion, when we have a uniformly varying load, the deflection at the free end will be equal to WL cube by 120 EI into 15L minus 4A. Similar way, when we have the same uniformly varying load, but up to some portion, and it is varying from 0 to W. 0 is at fixed support and W is at some A distance from the fixed support. So then the deflection formula at the free end will be equal to WA cube by 120 EI into 5L minus A. So this is a deflection formula. So these are the deflection formulas for a cantilever beam when they are subjected to a different loading conditions. The deflection formula has been derived for when at the free end. So these all formulas are related to the free end of a cantilever beam only. So these are some of the textbooks and references. Thank you.